This is lecture 6.5. It's all about how intermolecular forces actually determine the state of matter of different substances and the relationship between the particles in those different substances. So this applies what we know about intermolecular forces. As usual, you should do the learning targets before you start. So make sure that you've used your textbook and started working through some of this information. This in summary section here actually is things that you kind of should be able to pull together at this point from everything that you've learned in this lecture and the last one. So it's not really from somewhere in your textbook as much as it is let's kind of sort back through everything. So make sure that you've looked through these, that you've started them in your learning target notebook, and then that you are starting the video again when you begin. Okay, so here goes. The one thing I do want to mention is that I didn't really put this information in this lecture because it's kind of the ideas of the definitions of surface tension, capillarity, adhesion versus cohesion, and viscosity kind of are all just these ways that we can also apply intermolecular forces. And I really just need you to know the definitions for them. So please make sure that you've found them in your book. And if you have questions, make sure you ask in class. All right. I do want to talk about how your book divides substances into 6 different types of solids. And really most often as we divide things into categories here, we use 4 types of solids or 4 types of substances as our guide for the different ways that those atoms or molecules are held together. So I'm going to kind of talk more about them in these categories versus the categories that your book uses. But notice that really what's missing here is amorphous solids, what's missing from what your book includes, and atomic solids. So those two are kind of loosely included in some of this, as well as similar to some of these. So I kind of, most of the time College Board doesn't divide them out. So notice that we're talking about ionic solids, molecular solids, which often, like the noble gases, like atomic solids, are often included in the discussion of molecular solids because the forces that hold them together are the same. And then amorphous solids could be typically might be molecular, could be network covalent. So we start to see those in maybe both of these. And so we're going to kind of lump them into those bigger categories as we talk. I like this image because it gives you the image of the pictures of where the atoms are compared to each other and the molecules between things, etc. So that kind of gets you started. Okay, so your book defines atomic solids as mainly the atoms of noble gases. And remember, they're noble gases because they are typically gases at room temperature. So we would have to really lower the temperature or increase the pressure to get them to become a solid at all. This is because if they were to be held together, they would be held together by intermolecular forces, and the weakest ones, London dispersion forces only. So it totally relies on the temporary movement of the electrons to go to one end or the other. If we were comparing the boiling point of helium to neon to argon to krypton, etc., we would expect that the smaller noble gases have lower boiling points. And this would be because they are smaller, there are fewer electrons in each atom, so they are less polarizable. And remember that that's your terminology for when you're doing London dispersion forces, is that you want to be talking about the number of electrons or the polarizability of the electron cloud. So it's a less polarizable electron cloud. So if I were helium, like helium is smaller, and then maybe argon or krypton is larger, then helium definitely has a lower boiling point than argon. And so we would talk about it from those reasons. We often will find those mixed in same questions as molecular solids, and that's because it is the intermolecular forces that still come into play. So these are, of course, atoms in the molecule are held together by covalent bonds. So you can see that in here, that in this image we have these covalent bonds that are holding the molecule together, right? And then in between the CH4 molecule and the next CH4 molecule, are the intermolecular forces. So remember that these are relatively weak in comparison to covalent bonds, and that they give us a variable state of matter. If something's held together, it's a pretty small molecule and it's only held together by London dispersion forces, then it's going to have a really low boiling or melting point compared to something that is a larger, more polarizable molecule, or maybe a permanently polar molecule, a dipole with dipole-dipole forces, or maybe even a larger molecule with hydrogen bonding capability. And so, so that's kind of the reason there's so much variation in states of matter. Some things that you do need to know about these is that they never conduct electricity, and that would be because even if we get them dissolved or we make them so that the particles can move across each other in a liquid form, there are no charges here. This is, even the polarity of molecules is not enough charge differential to conduct electricity through that substance. So most of our molecular solids do not ever conduct electricity, and a few of them might be very slightly electrolytic, or be slightly small, weak electrolytes, but is rare. So we typically talk about that as a non-conductor. Also, solubility then depends on the polarity of the solvent and the solute. So we'll talk about solubility in a little while, but know that if something has charges, it needs to have something with charged particles or charged regions to be able to form new attractions. And so solubility definitely depends. Polar substances can dissolve other polar substances, or will dissolve in other polar substances, and non-polar solutes will not dissolve in polar substances, and vice versa. So we want to be really careful that we are looking for polar dissolves polar, but non-polar can only dissolve non-polar, and so that's important. All right, ionic solids are networks of ions. This is a three-dimensional network of ionic bonds. So remember that ionic bonds are simply attractions, but they're pretty strong. In the realm of positive to negative attractions, they are stronger attractions than hydrogen bond attractions. So they are the strongest of all our positive to negative attractions, and that's because of the total transfer of electrons, a complete positive or negative charge versus the partial positive or negative that we see in dipole-dipole forces or hydrogen bond forces. So this is a really important thing. The reason that ionic solids are so solid is because of the three-dimensional network of those ionic attractions. And so we'll look at crystal structures in a second, but definitely if it were just one positive to one negative, that attraction is strong, but not strong enough to really hold it together a lot. It's because we have so many ions in a three-dimensional network that it gives them really high melting and boiling points. They are solid at room temperature, and that's because the attractions are strong and in three dimensions. However, if you hit them, they are brittle. The bonds shatter kind of all at once, and I really like this picture because what happens is that when you put some stress on here and slide all these ions over, now all of a sudden the positive ions and the negative ions are next to each other and will repel each other. Okay, so this happens instantly if you were to hit it or try to put it in a mortar and pestle and grind it. Then what happens is that you're actually making those positives and negatives try to slide across each other, and then they push each other away. Unlike in metals, where when they slide across each other, the electron C just kind of holds them together. When they're solid, the ions are trapped in position, definite set positions. So that means that when they're solid, they can't conduct electricity. But if we dissolve them in water and now the ions are flowing around in solution, or we melt them, we say that word as molten, as in melted, then ionic compounds are able to conduct electricity in either of those situations. So be on the lookout for that, because you definitely want to compare that to molecular solids, which never conduct electricity, and metals, which always conduct electricity. So you definitely want to pay attention to the differences between that. These show up a lot in free response questions. Just so that you kind of have an idea, there's several different kinds of cubic structures. And most of the time this is pretty confusing, and there's not a lot of, if you look this up, there's a lot of math that goes with it, but College Board doesn't expect you to see the math. College Board just expects you to know, is the cube body centered, in which case the atom or the ion is at the center of the cube, or is it face centered, which is basically each of these atoms or ions is at the outside of the cube, right? So that they're basically cut in half. So this is a little bit confusing. It's not something that is super important, but it is something that you want to try to picture, that depending on the ratio of ions to each other and the size of the ions, etc., you can see how body-centered cubic or face-centered cubic might make a difference. So, so that's kind of an important distinction between them. Okay. Metallic solids, this is review from the 5.5 lecture, and remember that sea of electrons that's around all the metal nuclei allows them to conduct electricity. Pretty much metals are already flowing electrons, so conducting more, putting one more in and having it push all the way through or be drawn through is really nothing new for them. They are malleable and ductile because, unlike ionic compounds, when this occurs and they get pushed against, that sea of electrons just surrounds them all in their new positions. So they're flexible. And that also means that even though their melting points vary greatly, they have pretty high melting points because those nuclei are held together by that sea of valence electrons. Of course, the moving electrons also gives them luster, kind of as an art photoelectric effect. So this is kind of what we want to know about metallic solids. You cannot really identify them usually by their melting point, but you can by electrical conductivity and by the malleable ductility versus brittle. Okay, and they will not dissolve in water. Sometimes they will react with water, but they will not dissolve in water. Okay, and I didn't put that in the notes. Okay, and network covalent solids, this is something that can be kind of confusing for some people, but these are built more like ionic compounds in that they're three-dimensional networks of atoms, but they are atoms that are covalently bonded, not ionically bonded. So the difference is that even though it's a three-dimensional network, just like in an ionic solid, this is a real bond. This is a sharing of electrons. This is not what we call an ionic bond, which is really an attraction of a positive to a negative. So these bonds are the strongest. Covalent bonds are the strongest of our bonds. And so these structures actually usually have the highest melting and boiling points. Maybe they are the hardest. They are the most with those structures set in space and where they're going to be. So this is a really important distinction, is that their melting and boiling points are often higher even than ionic compounds. They will never conduct electricity again, even if you melt them, and that would be because they don't have the charged particles to allow the electrons to transfer through. And unlike most ionic compounds, they are not soluble in water. This is because these are covalent bonds that are strongly holding together those atoms in a network of a bunch of molecules that are not even considered individual molecules. And so there's not really a way for the water to get in between and form new attractions, or for them to break off and get in between the water and form new attractions, which is what has to happen in order for it to dissolve. Something that you should know is that these you got to be on the lookout for, because it will be solids that are made of only pure carbon, like diamonds and graphite, or they are pure silicon, or they are a combination of the two in silicon carbide, or they are SiO2 silicates. And we'll talk about a different kind of silicate in a minute that's not built like the network covalent. So you want to just be on the lookout for silicates in particular, quartz, etc., sand. Those are network covalents. So be on the lookout for them. I do want to draw your attention to the fact that this could be three-dimensional networks of covalent bonds, like in diamonds here, right? Or like they show up here. These are three-dimensional networks of what's going on. Or they could be two-dimensional networks where these are all flat and it forms a flat sheet and a flat sheet. Diamonds, of course, are very, very hard, and that is because of this three-dimensional network of tetrahedral bonds of carbon to carbon to carbon to carbon. And those bonds would be nonpolar because they're all carbon. And so there's not really any attraction to anything else. But if we're talking about graphite, in between these sheets, we have London dispersion forces. These are also nonpolar. It's just that now these are bonded in a trigonal planar sort of configuration instead. You can see that if you look carefully around one of the carbons in here, you can see that there are 3 bonds around the carbon center. And so this trigonal planar makes this nonpolar, but the sheets are held together by London dispersion forces. And they're pretty strong because in those sheets it's strong enough to make it a solid, definitely at room temperature. So graphite in your pencil, when you write, it basically peels a sheet off and peels a sheet off and peels a sheet off. So after so many sheets are peeled off, you have to sharpen your pencil. So this is how that works. They're both network covalent. Notice that amorphous solids can be a bunch of different types of things. So we do see silica, SiO2, as opposed to silicates, SiO2, or silicon dioxide there. And it can be in a more amorphous structured pattern. So if it were in a crystalline solid, like a network covalent solid that's really hard and doesn't conduct electricity and doesn't dissolve, etc., compared to this amorphous solid, this is a lot looser of a structure. And they kind of vibrate in place and more random arrangements, and then that means that I might be able to break a few of them and form new ones, right? If I break a couple and form some new ones. And so picture rubber bands as amorphous, but also picture glass as amorphous. It's pretty stable, but know that if you have really old windows, like 250-year-old windows, the bottom will be thicker than the top, and that's because that solid is amorphous, and over all those years has kind of gravity has kind of pulled them all into place. So these kind of overlap between a couple of different things. Amorphous could be covalent, network covalent. It could be a crystalline solid that is less regular. So it might not be network covalence, could be sugar type or other weaker intermolecular force type, but it's okay. We'll not worry much about them. So in summary, why do we care? What I want you to look at is that our intermolecular forces are always weaker than our intramolecular forces, which are between molecules. And the covalent bonds are very, very strong, and they are most often as strong, if not stronger, than ion to ion. So I'm not a big fan of this idea. Notice that they're very similar, and you want to kind of keep that in mind. And so it depends on the three-dimensional nature of it as to what's happening around that. So network covalent definitely is comparable to ion to ion. Also notice then that we have London dispersion forces here, and dipole-dipole forces here, and hydrogen bonding here. Ion dipole attractions are weaker than ion to ion attractions, notice. But this is because one of those is only partially positive or negative, that would be the dipole, whereas the ion is completely positive or negative. Also know that we have these attractive forces everywhere, between everything, unless something is truly behaving as an ideal gas. So it's seldom, remember. So just kind of keep this in mind. Be super, super careful, because remember that you're talking about within molecules or between molecules, and the within molecules are your answers for ionic compounds or for network covalence, right? But they are not your answer for anything that is a regular molecular substance or atomic substance, etc. So be super careful with how you're using these. And then, of course, now the reason we really care is because the stronger the intermolecular forces, or if we're talking about ionic or network covalent, the stronger that bonds are that hold that structure together, is the greater the boiling point, the greater the freezing or melting point, the greater viscosity. Remember, viscosity means resistance to flow. So the less likely it is to flow quickly if it's a liquid. It flows less easily if the intermolecular forces are stronger. That should make sense. It takes more energy to vaporize or melt. That would be heat of fusion or heat of vaporization's tie-in. It has a greater surface tension. If there are stronger intermolecular forces, you can resist coming down through the surface more, or it can hold together tightly. That cohesion at the surface is greater if there are stronger intermolecular forces. And of course, that means all those things means it's more likely in all other conditions compared to be a solid or a liquid instead of a gas. So this is the way we pull it all together, and we use a lot of our discussions about comparison of inter and intramolecular forces in our answers in this section. The last thing I want to talk about quick is solubility. There's a really big statement that everyone always uses that's like dissolves like, and it is not enough just to say something is soluble in something else because they are similar. You have to say what's similar. You have to be able to talk about if it's an ionic compound or two polar compounds, then how that polar molecular compounds, then how that allows those attractions to break and reform. So that's really, really important. But I really thought this was a great way to end, that you can always think about polar will dissolve polar, nonpolar will dissolve nonpolar. Polar will dissolve ionic because of the charged nature of it, etc. And then, of course, stupid chemistry joke to go with it, the polar bear and the grizzly bear, and pictures of oil and water. Remember that oil is nonpolar and water is polar, so the oil cannot get in between the attraction of the hydrogen bonds from water molecule to water molecule and stays separate completely. Whereas your ionic substance can get in between these water molecules and actually form new attractions with the ions to the water molecules and be able to dissolve. So that ends this lecture. Make sure that you're ready to really dive in and use this as we start answering some questions.